Oh, hey, Bob. Good to see you. How you doing? And before we get started, Bob, I have to tell you, and you tell me if I'm speaking for you. What we're about to talk about, the opinions are our own. They're your opinions. They're my opinions. They no way reflect the ISA St. Louis section, our employers, anything we deal with. These are our opinions. Do you agree with that?
I agree with that. They are our opinions.
All right, and we have several opinions. So, all right, thanks, Bob. We'll get started. So, everybody, hello. This is Jeff Blair and Professor Bob Heider. We're going to call this the Fixer. Our goal here is we're both part of the ISA St. Louis section. Bob Heider on the other end, and on the other side of the St. Louis metro area from me, has over 50 years in the process instrumentation, process automation industry. Myself, I'm going on about 15 years worth of instrumentation sales experience. Love it, and hopefully we can all learn something here today. But Bob, I'm going to turn it over to you. Can you tell the audience a little bit about yourself and your experience, please?
Well, I graduated from Rolla in 1966. I got a BS and double E and went to work for Monsanto over on the east side of the Crumrick plant. I was there for 12 years and moved to the corporate engineering. And I was there for many years until they busted that up, and I went to ag engineering and went there until essentially the end, which was 99. After that, I started teaching at Washington University and Digital Process Control Lab, and I did that for about 15 years. Also had several grants and research work and consulting assignments up until about a year ago, and then I finally decided to semi-retire, if you will. So that's kind of where we are. I was able to get a wide breadth of experience in my professional career. I've seen everything from heavy chemicals all the way up to pharmaceuticals to silicon, so textiles, the whole bit. So 96, I got a master's degree at Washington University. It took me 5 years of evenings, and so I was able to get that, and that kind of allowed me to get the teaching position and a few things like that. So that's pretty much my professional career. I managed to get elected to ISA Fellow about 10 years ago or so. So that's pretty much where I am.
So you've got some pretty heavy credentials, I'd say, and going throughout. I used to travel North America and Canada, and there's quite a few engineers out there that I think you trained either mentoring at Monsanto or teaching at WashU.
Oh, that's interesting. Yeah, I didn't realize.
There's a lot of Heider disciples out there. It's amazing what happens. So, well, today we're going to talk about one of the subjects that Bob has tried to impart some of his knowledge and teach me. So we're going to, from a simple standpoint, this little piece of metal is what we're going to talk about. They're not always made of metal, but this is a stainless steel Thermowell. So you'd put normally you'd put an RTD or a thermocouple in here, and then this would insert into the process. This happens to be a threaded thermocouple, but a Thermowell, I'm sorry. But so, Bob, can you tell us a little bit about Thermowells and maybe what happens when you don't use them, or they go Thermowells gone bad, I guess you could say?
Well, one of the interesting aspects of these is the fact that there is an error. There can be an error. In some cases, it's very small, but in other cases, it can be very severe, depending on how it's installed. And because actually you have heat that's actually conducting one direction or the other, depending on whether the process is hotter or colder than the ambient. Mm-hmm. And if you think about your days in high school chemistry or whatnot, and you had a beaker and you needed to know what the temperature was, you always found that if you stirred it around, you would get a more rapid and indication of what is the temperature is. So I have, as a result of a couple of cases where there were some significant errors, or at least I was able to perceive that there were errors in the thermal wells. Many cases these were installed in processes and in locations that were such that I didn't feel we were getting a decent temperature, so I developed this spreadsheet to give people an indication as to what the potential errors were. The other aspect of this is the dynamic situation and the fact that you take this piece of metal, and if you have a change in process temperature, it takes a period of time for you to actually get the element to respond to the process conditions. So I developed this spreadsheet, and what it does is it calculates the tip error. So as we move down here, you see there is the insertion length, and then there's a fitting, which can either be screwed or flanged. Mm-hmm. The part that's immersed in the fluid is usually called the insertion length, and by convention, it's called U.
The U length.
Now,
okay.
In many cases, you have insulation that you have to contend with. So there's a section called a lagging section. Mm-hmm. Before you actually get to the connection where you make the thermal couple or RTD connected to either a transmitter or goes into wire for some other. So basically you have heat conducting across this. You have heat from the tip all the way along the whole shank, all the way out or back in, based on mm-hmm. the fact that you have this inserted into the process. So the background for this, I'll give a background, is some of it is actually in this text here, which is called Transport Phenomena, which is a classic chemical engineering textbook on heat transfer. And mm-hmm. they have a section that discusses this and also the fact that there is a tip error. And back in 1980, there was a paper given by a fellow named Dan Richmond, who worked in Anheuser-Busch at the time. And this ISA paper actually discusses this error and shows you how to calculate it. So what this spreadsheet does is actually calculate that error. Mm-hmm. And the dynamics are based on another paper, which is by a gentleman called Buckley. And this was, I can't recall exactly when this was written, but at any rate, he wrote which is actually referenced quite a bit in terms of the dynamics of the well. So that's how the background of this, and so basically it's a spreadsheet that lets the user calculate what this error is. And in some cases, particularly where you have a stubby well, which now, as a result of the new ASME vibration standard, in many cases the user has to use a shorter well. And if they use a shorter well, they could potentially get some errors in measurement. And that's what I'm trying to call people's attention to here.
Interesting. So my experience with thermal wells going back and it's probably pretty standard to what most manufacturers or salespeople have seen. When customers order a thermal well, the documentation they typically want is a wake frequency calculation, which essentially means we want to make sure that this thermal well is not going to essentially wobble loose or become some type of we want to know what the vibration is going to be from the fluid going by. Is that in any way related to the issue we're talking about? We're talking about the heat from here to here, but as that fluid's coming by, and you get the wake frequency, or you get, it can potentially vibrate it. What does that fluid coming by do? Do we want a good mixture of fluid? Does that help with the heat dissipation, or just?
Yeah, right. The heat transfer is obviously better if you have an increased velocity. As I say, when you're having a beaker of water or a solution and you're trying to get the temperature, you kind of stir it around. This spreadsheet doesn't cover this standard, by the way. This is the ASME standard. To do a typical thermal well with that takes about 4 pages of calculation longhand.
Oh boy.
I've done it. So it is a fair amount of work. Most of the vendors supply this information, so you have to take faith that they've done it right. And I won't say any more than that.
Okay.
But no, I don't do that calculation in this spreadsheet. I decided that it's best, there's enough in there as it is now anyway, with just being able to calculate the air and the time constant, the thermal time constant.
So in your years of experience, were there any rules of thumb, so to speak, that, golden rules regarding thermal wells, such as they had to be so long or welded or threaded or a certain type of material?
Yeah, basically, in the first place, as far as the insertion length goes, it's usually a good rule of thumb is around 6 to 7 diameters of insertion length is a good rule of thumb for insertion. As far as the connections go, quite frankly, because of flammables and this kind of thing, you obviously are in a flanged. I would never use a screwed connection on any process. It's just my personal preference. I just feel like any process connection should be a flanged connection and not a screw, because if you cross the threads, you've got a real problem. And if you have a threadlet or something welded in, you'll have to cut that out, and that's extra expense. So in the case of a flange, it's just it's 2 flat surfaces that get bolted together, and if you happen to cross one of the bolt threads, well, you throw it out and you do another one. So it's essentially, I just have a firm belief that one should use flanged connections for any process fluid. That's just my thought. So those are 2 of the rules of thumb that go along with it. There's a lot of discussion about RTDs versus thermocouples. I don't think into that today, but at any rate, there's some opinions on that. But basically, those are the other thing is, as far as the material, the construction go of the well, you need to, in general, you need to think about good heat transfer as also process corrosion considerations. And generally, we like to make the well to be a little bit better material of construction than the process piping spec. So that's the other thing that goes along with it. So the process piping spec was carbon steel. We usually go with like a 304 stainless or something like that.
So we don't call you the fixer for nothing, Bob. I'm curious if you went to any job sites where you got called out to go to a site, and maybe you showed up and they had either the wrong type of thermal well, or maybe they had threaded thermal wells in the process instead of the flanged or welded connections. Did you ever get to chew anybody out and rip tell them to rip out that thermal well and put it in the right thing?
No, but I did have some cases where people didn't understand the dynamics of it. We had a glass-lined vessel a number of years ago that had an incident. It overpressured. Now, they didn't say it was an explosion. They just said it was a situation that needed some attention. So basically, the rupture disc blew, and so the pressure did go up, And at the same time, the temperature appeared to lag. And I got a call from the investigating team. They said, well, we were looking at the chemistry here, and the temperature seemed to be, it should have been higher, and they didn't understand why. So I had to acquaint them to the fact that there's, in this case, there was a piece of glass at the bottom of a baffle section, and it had a time constant was like a 2 or 3 minutes, something like that. So so those are cases where that was one that I recall where it was important to understand something about what was really going on here over and above just another spec that needs to be installed or something of that sort. So that was one where there was another situation I recall where an engineer had installed a very short thermal well in a section of ducting that was about 10 degrees off in air. Once I went through this spreadsheet and explained it to the people as to what was going on, and left them with the spreadsheet so they could realize that their temperature was actually about 10 degrees cooler than it should have been. Okay. So there's a couple of them where I didn't do it to every well I had, but there were some where I thought there might be a problem. I would go through and run these calculations just to make sure that they were reasonable.
I know, talking to you, you've got some horror stories from the field, and maybe we can save those for a future recording for everybody to hear. So back to this. So back to the thermal well. So we're talking about the temperature here is different than the temperature here. Is the spreadsheet I showed on screen here something that we can put on the website for users to download? Is this something? It sounds like it's got some practical experience.
There's nothing confidential about it. Just
take another look at that.
If anybody wants to use it and beat it up, that's fine with me. But I probably should explain to you how it works.
Sure. You want to do a quick walkthrough?
Yeah.
Okay.
So you open up this spreadsheet, and the first thing you see is a series of a column here that has either light blue or green entries, and this is where the user has to put in the data for the thermal well. The red cells are calculated cells. You'll notice that there is to the right of this a material table, and this is a lookup. So basically, depending upon the material of construction, you put an X in that box next to whichever one you want. A capital X, by the way. It has to be a capital X. And if you want to void out another entry, you have to put in a space. So it's just essentially the way the lookup table works. So that then will actually bring that data into the well materials of construction. So you have the well dimensions and material of construction. The next thing you need is the fluid properties, the density, specific heat, and thermal conductivity and viscosity. Those get entered in. The other aspect is, since we're actually calculating, what we're trying to do is calculate how much heat is being lost through the well. So
how much heat is being lost through the well? Okay.
Yeah, so we actually need to know how much is lost through the weatherhead. So you have to take an estimated, you put in the ambient temperature, and you estimate the area of the weatherhead, or it could be a transmitter. Whatever, you have to put that in square feet. And then essentially estimate the heat transfer to the air. I use 7 BTU units here, which is a reasonable one for just to the ambient air. The next information that's put in is information about the detector. There's the the annulus thermal conductivity, there's a specific heat of the detector density, in this case it's magnesium oxide, and the detector diameter, and that's in feet.
Okay.
So once you enter all that information in, the thermal time constant is calculated. You don't have to use the solver for that. So those numbers are actually calculated based on Buckley's paper. Now, I did modify the fact that the newer wells are spring-loaded. So I assume that the user has a well that has a spring-loaded element into it. And the bottom of these wells now is gun drilled, and there's a V or a W, if you will, at the bottom of the well. So there's very good connection between the element and the bottom of the well. That used to not be the case. In days of old, we made our own thermal wells. And we actually had to, we made our own thermocouples, and we actually had to put a little motor oil in the bottom of the well to assure that we had good heat transfer. So, but in today's day and age, the newer wells, I've had good luck with the elements just being spring-loaded to the bottom. It makes it fairly receptive. So once all that is entered in, to get the tip error, you have to use a solver. The solver is on another tab in the spreadsheet.
Let's go back. Okay, so we're back to the spreadsheet. So when we click on, we've got the entry, we put all our data in there, and then we go to Therm, and we see we've got these heat flow calculations in a solver cell.
Yeah, so that needs to be 0. To balance all the heat. So to do that, you go to data and then solver.
Data,
yeah.
Solver, and then we hit solve.
Right.
This is new for me. So what
can
you walk us?
Yeah. Then it goes through and it just tells you to keep the solution. You saw that it goes to 0, so then you hit OK.
Okay, keep solver solution, answer sensitivity limits. Okay.
And then if you go back to entry, you'll see where what the error is up at the top part of the cell. So in this case, it's 1/10 of a degree. So what we can do to show how this works.
This is what we're looking at right here, Bob. 1/10
right,
of a
that's the
Fahrenheit.
error. So let's go ahead and make a case of making it out of copper instead of stainless, just to show that it does work. So hit an X, a capital X there in copper. Okay, and then then come down to the stainless X and right. Okay. So now go back to the Therm tab again, and go into the solver again. Okay, keep that solution. Hit OK there. Then go back to the entry.
Oh, quite a much bigger error.
Yeah, you'll see that was a pretty extreme case, but it does show that the spreadsheet does do what it supposedly what it's advertised to do. So that's pretty much what was put in with this. I do have another spreadsheet that actually, this is for a flowing well. I do have another spreadsheet that's based on the fact that a well is in a stagnant solution. That one requires a calculation or understanding of what the fluid buoyancy is, which has to do with what effects you have in terms of heat transfer across a liquid that's buoyant because of temperature change. So that one is a little more involved, but you can actually calculate the error and the time constant in that case. Just as a side note, that was one of my experiments that I had the students do in my lab. I actually had a Thermowell, and I had them go through and calculate the heat transfer, and then also calculate the time constants. And then they would actually store the data and then get it into Excel, and then calculate and measure the time constant. So, and compare with their results. So that was a good exercise in. Actually, it was more an exercise in transport phenomena than it really was process control. But the one thing that you need to think about with this is that in many cases, the thermal well is the biggest lag in the temperature control loop. If you take a steam heat exchanger as an example, and you're heating some fluid, and you have a thermal well downstream a bit, the chances are, when you go through and analyze this, the thermal well will be the largest lag in the system. Now that's lag, that's not dead time. You have dead time is just the velocity in the distance, if you will, between the exchanger and the well. So you might have some dead time, and you'll have a little bit of dead time through the exchanger too. But in terms of the overall lag, in many cases, my experience has been with temperature control that the thermal well itself contributes to the largest lag in the system. So that's another one to be concerned about.
I remember when I started in the business, I can't remember the specific application, but the customer was adamant about using bare elements with no thermal wells. They said that was quicker response, more sensitive. The thermal well, to your point, it was a lag. It deadened the sensitivity of the element. You ever seen anything like that where you had?
Well, I have seen cases where the plant insisted on cutting the end of the well off, which basically I really got upset about that, and I told them that I insisted if they were going to do that, that they actually weld the element to the well and put a stainless steel tag on it.
Oh my.
Yeah,
What was the reason behind that?
Well, I didn't want them to take the element out and think that it was a well. In other words,
cutting the end of the thermal well off just for the sensitivity, or the.
Yeah, it made it. It was much more sensitive that way.
Yeah.
And the idea was that this was for a steam desuperheater, by the way. So the temperature had to be very responsive, because they were actually, with a desuperheater, they were actually spraying in a bit of condensate into the steam line to lower the superheat. So as a result, they wanted a very, very fast loop. And what they did was they cut the end of the well off. And as I say, I was very concerned about doing that, insisted that they back weld the element to the well, and so that no one would ever actually come up there and think that, well, I can just take, if the thermal element was bad, I'll just go up there and put another one in without, in that case, it was completely unsafe to unscrew it under steam or something like that. So that was my real concern about that. I actually really would strongly discourage anybody from ever doing such a thing.
Makes sense. Bob, we wouldn't be doing our jobs if we didn't talk about the future of temperature or thermal wells a little bit. Any idea for what the future holds for temperature measurement, or can you tell us about anything you see?
Well, there's a move by another major instrument company that actually has a product that will actually measure the temperature of a solution in a pipe by directly no well at all.
Mm-hmm.
And they mount this on the pipe.
Surface mounted elements.
Yeah, and this gets into a case of, well, I don't know the details of this as to whether obviously if you're depends upon the ambient conditions and the amount of insulation that you have and a whole series of other aspects of this. But I think with the smart element of smart instruments and this kind of thing, if you had some intelligence that went with this in terms of the weather barrier that you had and the amount of insulation that you had and this kind of thing, you potentially could come up with a product that was reasonably accurate to measuring temperature that way. The other thing that's happening with Thermowells, there's another company, maybe a couple of them, that now actually put spirals on the outside of the wells to limit the vibration. If you actually are driving around someday and you look at smokestacks, you'll see in some smokestacks they actually have a band that goes around it. And the idea of that is it just breaks the wake. So basically you don't have the vibration of the stack. And that's essentially what they're doing in wells. So there's I've seen some of that. But as I say, I think the big thing that kind of shook people up was this ASME standard that came out in 2010, redefining the standards for a thermowell vibration, because the first set of spreadsheet calculations for those were very, very simple to do, and now they're much more involved. So.
I think I'll ask before I go into that. I appreciate the feedback on the future. That makes good sense. The breaking up the wake frequency and increasing the reliability overall with the spirals and things. That's a neat idea. But I'm going to ask you. You showed us a few papers. I'll get with you after this, and maybe we can make those available for download, or at least have the reference link to it when we post this on the website. I got to tell you, Bob, what I took away from this when I talked to my family and they said, "What did you learn talking to Bob today?" You know what I'm going to tell them? I'm going to say, "Did you know they used to put motor oil in the bottom of Thermowells back in the day?"
Yeah.
So that 10W30 in my garage, it's got a dual purpose, but we'll keep it in the car for today. But this has been really interesting. Bob, anything else?
Well, that's about all I can think of. If I think of something else, and the problem I have is occasionally I'll wake up at 2 o'clock in the morning and say, "Oh my gosh, I should have written that up," or "I forgot about this case." The one thing about the dynamics that can be improved, and I have that in the write-up on the spreadsheet. One of the things you can do with the newer DCS systems has what's called a lead lag block.
Mm-hmm.
So basically you have this thermowell lag time, and if you put a lead lag block in between after when you bring the input into the DCS system, and you have the lead be equal to the lag, or it can actually be slightly greater than or slightly less than, this will improve the response. Now you'll have to have a lag time, and the general number I saw for that was 40%. And this appeared, I saw referenced in a text, and it was for an old pneumatic system that was made by Taylor Instruments. They had this, what they called some sort of a thermowell compensator, which actually was a lead lag, and you actually screwed in or whatever to get this to respond, to take into account the effect of having the lag in the thermowell. And my guess is that was probably pretty hard to maintain being pneumatic. But with the current DCS systems, this is outstanding because you simply put a block in there, and you have you can have the lag time. If it's slightly greater than the lead time, you'll get a bit of an overshoot with it. So that may cause some problems. So you probably will want to have it to be the lead time to be, say, maybe 90% of the Thermowell, and then the lag in that lead lag block should be about 40%, is what the number that Taylor was saying at that point. And I have a curve of what that looks like when I set it up in the lab by putting one of those in. You get what happens is the response is such that you get closer to the set point to the actual temperature faster, but it still takes you the same amount of time to get to the exact temperature, but it does improve the dynamics of the loop. So that is one thing that I recommend people do if they have a Thermowell with a fair amount of lag in it. This will at least get you to a point where you can compensate for that.
So compensate for the Thermowell using the lead lag and the DCS. Okay. One more thing, Bob. We have just a couple more minutes, but you and I have talked about several topics over the years. You've taught me a lot coming to the lab there at Wash U, and just some other topics. I know maybe when we post this video, we could put a feedback section and get what other topics people would like to hear about most. So I'll throw a couple things out there. Let's make sure that these are things you'd be interested in talking about your experiences. How about DP flow and orifice plates?
Well, yeah, I've got some spreadsheets on that. I've actually took some of Spinks's calculations and put them in spreadsheets. And the reason I did this was many times I would get in the field in a startup and the meter hadn't come in time for startup, or we started up and the meter didn't work, so we had to put something in that we knew would work. So we know that an orifice plate in most cases will work, assuming it's a reasonable viscosity and a reasonable velocity in the line. So basically I ended up, because we didn't have orifice flanges, we had to order those, I ended up with just putting a orifice plate between a regular set of flanges and using 2.5 by 8 diameters or vena contracta taps or whatever. And I've, through the years, I've developed the spreadsheets to do those.
Cool.
Those ends up being just a series of lookup tables.
So that's a good topic.
The other thing I've noticed is that despite the fact of all these newer meters that are available, orifice meters are still one of the most commonly used instruments for flow. Tried
and true, that's for sure. How about, I think you had another word for them. I call them bubblers, level bubblers, but what'd you call them? Spargers?
Well, purge pipes.
Purge pipes. Is that a good topic?
Yes.
Something you'd like to talk about?
Yes, I've where we had cases of level instruments that didn't work. We ended up having to put in
that never happens.
purge pipes.
That never happens. They always work, right?
Yeah. So that's another, the other aspect of this is if you consider using orifice plates and purge pipes, you end up for pressure and level and flow, you can use one instrument, which is the DP cell. So the DP cell can actually serve as a single instrument for the entire plant for level and flow and pressure. If you vent the low side of the DP cell, it then becomes a pressure transmitter, which is, if you vent the low side, by the way, be sure to put a bug screen there so you don't have a mud dauber get up in it. That's another aspect. So those are, as I say, I've had a lot lot of experience. I don't know how many DP cells I put in, but that's sort of my first way of actually thinking about it. If I have level, I always think about putting in a purge pipe because I think that's the most reliable. The other thing about a purge pipe, by the way, is the fact that if you have a problem with the instrument, you simply shut the valves off, tag it out, and you can remove it for service. If you have a radar or something like that mounted directly onto the tank, if you have to take it out of service, you have to get a tank entry permit. So
well,
those are another aspect of that.
Well, let's take some feedback and some comments, and for today, we'll finish up this episode or video log or whatever we're going to call this for our ISA St. Louis section. So, Bob, thanks very much. We'll say goodbye to you, and we'll talk again in here in another couple weeks.
All righty, take care.
Sounds good.
Be sure
Thanks.
and vote.